So I say welcome to today's webinar where we have the pleasure to listen to Åsa Östlund from Tree To Textile and Andreas Bengtsson from RISE. And my name is Maria Ulmhult, and I am a project manager and work also with business development at RISE and on the test facility Lignin City. The reason that we're here today, or thanks to the project called Lignin for Future that we do in collaboration with Sting Bioeconomy, Paper Province, Kristinehamn Municipality and RISE as the main partners. It's financed by the Region Värmland and EU structural funds. And to have the best experience of today's webinar, you can check in your upper right corner and choose speaker's view. Then you will soon see the presentation from the speaker and also who talks next to it. And we kindly ask you to write your questions in the chat. You find it on the bottom of your screen, and type in your messages there, and we will take as many questions as we can after each speaker. And afterwards, we will stay for a chat. Eftersnack, we call it in Swedish. Then we will ask you to turn on your cameras and microphones as well. And when we listen to the presenters, then we are very happy that you keep your microphones on mute. But I will now welcome our first speaker, Andreas. You are the one we will listen to first. And you will share a presentation with us, and you will also introduce who you are. So welcome everyone to today's webinar, and especially welcome to Andreas first.
Thank you, Maria. Now we will see if I can share the presentation here. Is it the right or the wrong mode?
It's the wrong mode.
Okay.
But you know how to change it.
Yes.
So this is still very professional.
Okay.
Yeah.
So, Andreas Bengtsson, I'm a researcher at RISE. I'm working in the same group as Maria, in the lignin group or lignin unit at RISE. One topic that I've been working a lot with since I started off 6 years ago is bio-based carbon fibers from cellulose and lignin. So I will today present some of the work that we have been done at RISE over this past 6 years on bio-based carbon fibers. So let's get stuck in. I think a very good start is to just highlight what is carbon fiber. Well, it is exactly what it sounds like. It's very thin fibers or filaments comprised of more or less only carbon atoms. The structure of the carbon varies usually, but it is somehow close to a graphite structure that you have. And the structure in itself is the reason why you can have extremely high mechanical properties of these fibers. They can be super strong, super stiff, and they're usually also quite brittle. They have a low elongation at break. And this, together with the fact that this material has a low density, is usually why we call it a lightweight material, and therefore it's highly desired to be used in structural applications where you want to have this lightweight characteristic. So usually you blend carbon fibers with a polymer, thermoplastic polymer or a thermoset polymer, then you make a composite out of it. You can use them in wind turbine blades, aircrafts, sporting goods, and cars, and so on. And today it's mainly made from a fossil-based precursor, polyacrylonitrile PAN, but it's also made from petroleum pitches and to a very small extent also from cellulose. I will not have time to go through the whole history here, but the very first carbon fiber ever made was actually made from cellulose. And already in the late 1800s by Thomas Edison, actually. when he was developing the electric lamp. He used a graphitized cotton strand to to make his lamp. Actually, it's quite a fun story in itself. However, carbon fiber is manufactured by taking your precursor, so for example pan, and then you thermal treat this material in several steps: stabilization, carbonization, and sometimes graphitization as well at very high temperatures. And then you size the fibers, you apply a surface finish on the fibers, and then you wind them up on a bobbin, and then you sell this. Basically, the whole idea here in this process is to remove all the atoms except the carbon. So the carbonization step, for example, is done in inert atmosphere, so in nitrogen atmosphere, for example. It's a pyrolysis process, basically. And there are quite many details here to go through, but some of the key highlights I would like to mention here is that this is an energy-intensive process in itself. It's a continuous process, so the slowest step will be the bottleneck in the process, and this is usually this stabilization step, that it's basically an oxidation step that you do before carbonization. This is the slowest step, so very much research has been focused on minimizing the time here in this step. And actually also, if you work with different type of precursors, if you use pan or cellulose or pitch or lignin, for instance, exactly the conditions here, the temperature, optimal temperatures, times, how much tension you can apply to the tow will depend on your starting material and also the properties you want to have in the end of the material. Important to remember. So far so good, but there is one problem with this material, and it's very expensive. And this precursor is made from non-renewable sources. And actually, it's also so that this polyacrylonitrile precursor that dominates is also very costly. So you want to find a cheaper precursor. And that is what we are working a lot on at RISE. So we are looking into cellulose and lignin. I think that is an opportunity here. If we talk about lignin, well, it's available today from the craft process in high quantities. It has a high carbon content, which is good if you want to make carbon, because the yield, I didn't mention it, but the yield in this conversion process to carbon fiber is important because it's a very expensive process in itself. And then if I look on the cellulose, well, it's also available, dissolving pulp, for instance, that we can use. It's also a strong and linear polymer, which you can orient, which is important if you want to make a strong fiber. Lignin is amorphous, so it lacks this property. But what if we can combine these two together? That is what I've been working a lot with, a blend of lignin and cellulose in a precursor. And that is what I will talk about today. So if you want to make a precursor, carbon fiber precursor from a blend of lignin and cellulose, how can you do that? Well, perhaps the most economically feasible way of do this would be melt spinning, but this cannot be used because cellulose is not meltable, so we cannot melt spin it. Instead, we can actually use solution spinning to dissolve cellulose and spin fibers. I mean, this is viscose rayon fibers you have, lyocell fibers are produced by solution spinning techniques. And then the question becomes, we need to find a system here where we also can dissolve lignin. And this is something that we are working on a lot at RISE. So we have two approaches that we are working on. And one of them is to use air gap spinning. So we dissolve cellulose pulp and lignin in an ionic liquid. And then my colleague at RISE in Mölndal, Jenny Bengtsson, she's been working a lot with air gap spinning of lignin cellulose fibers. The very nice thing with air gap spinning is that you can produce highly oriented lignin cellulose fibers, strong fibers, and you can also dissolve high loads of lignin, up to 70% relative to cellulose in the final fiber. I would consider that quite high. The other approach we have is to use wet spinning, which is the other solution spinning technique. And here we are using we can also use a water-based solvent system. So basically water and sodium hydroxide under certain conditions to co-dissolve cellulose and lignin, and then use wet spinning to produce lignin cellulose fibers. The advantage here compared to approach 1 would be that we use a cheaper solvent that is it's easier to, because it's basically water and sodium hydroxide, easier to recycle and cheaper. The disadvantage is that the fibers are weaker and we cannot use as high lignin loads. We have been able to use up to 35-40% lignin most so far. I forgot to mention, but usually when you do air gap spinning, the approach number 1, you coagulate in water, but when you do wet spinning, we typically need to have an acidic bath to coagulate the fibers. So if we then move forward into how we can make carbon fiber from this. So when I started off, I worked a lot in small scale in lab. I call it batch-wise conversion. So basically put in some fibers in a muffle furnace, shut the door and heat it up to 250 degrees in air to stabilize the fiber, take the sample out, put it into a tube furnace and carbonize up to 1000 degrees and so on. This is good for initial studies, I would say, proof of concept, but you have a very important limitation here, or actually 2 limitations, and that is that you cannot stretch the fibers so much. You don't have control over that. And you usually also need to have slow heating rates that are not comparable to what you would use in reality if you produce carbon fiber. But much of the research being done is done like this, actually. But since I would say 2 or 3 years ago, I've been working more and more with continuous stabilization and carbonization to start to investigate how we would be able to produce these fibers in more industrially relevant conditions. So that is how we typically do it here. I want to share a couple of results as well. And the very first thing to ask is, what is the effect of lignin compared to pure cellulose? Because we blend in lignin here to increase the carbon content, and then it's of course logic to look on the yield. So this is the yield of carbon fibers made in lab from pure cellulose or from a lignin cellulose precursor based on a blend. And here we can see clearly that the yield increases significantly. I can also mention that the conversion yield usually for commercial PAN, fossil-based PAN, is around 50%. But we see a drastic increase here, and that's exactly what we wanted to see. And this is the same, but the first figure was for ionic liquid-based fibers, and here we can see for the cold alkali-based fibers, and we can see that the trend is the same, that we increase the yield if we make it from a blend of lignin cellulose instead of only cellulose. And to further address the yield, I can say also that we have been impregnating the fibers with some salts, and phosphate-based salts, they are flame retardants for cellulose, so we can actually increase the yield even further. I will not go into detail about this today, but it promotes this. Certain compounds can promote charring of cellulose, particularly, and this is also affecting the yield. This is what I show here. How about the mechanical properties then? What we have seen as a generic result, I would say, is that typically you will decrease the precursor, the mechanical properties of the precursor when you blend in lignin. So the red circle here is a pure air gap spun cellulose fiber, but for a blend you see it drops, the modulus and the strength goes down. However, after carbonization to carbon fiber, usually we do not see any significant difference. And I would say this is also true for the cold alkali based system. And well, is this strange, or can we expect this? Well, what we do when we carbonize, convert cellulose and lignin into carbon fiber is that we completely destroy its structure, in particular cellulose. But then we build up a new carbon structure. So I would say a very interesting question is, does it really matter how we spin? To be continued. I mean, I think it's an interesting thought here. We're not so sure yet. So going on a little bit, I just want to mention this about continuous conversion. So we work nowadays mostly with this type of equipment. And the reason is that we want to be able to understand how we should produce these fibers if we scale it up to a commercial production or someone do it in the future. And this is a quite primitive setup. It's basically a winding system and a tube furnace. We can control the speed and the relative speed to stretch the fibers. And we also have installed a small tensiometer. And we have learned a lot with this one. We can stabilize one day and then we decarbonize the other day and so on. So we do it. It's not a full continuous line. Usually you have them in series, several furnaces, but I would call it a semi-continuous equipment. Here we typically work with fiber tows of a few hundred filaments. And it may seem trivial, but if you take into account the fact that there are so many parameters here. You have the temperature profile, you have the time, you have the tension, you also have a gas flow here, and you also have your precursor composition, and you have several steps that you do this in. The amount of combinations you can try is enormous. So, and these experiments take time. So it's not so trivial actually. And I just wanted to take one quick example. When we started off, we could we did a lot of comparison with batch-wise experiments. And as I said, the heating rate in the batch-wise equipment is very slow. So usually the conversion time differs substantially. And we could not stretch the fibers very much in the beginning. But however, we got the same strength of the carbon fibers, but we could not achieve the same Young's modulus, the stiffness of the fibers. So until I would say now, the conclusion has been that we need to work more on this, try to develop different conversion protocols. How and when can we stretch the fibers to maximize the mechanical properties? That is something that we have been working on a lot this past 2 years, I would say. And to bring up some general conclusions from this work, I would say that we can make bio-based carbon fibers. We are quite confident about that from these lignin cellulose precursors, and we can use commercially available raw materials. The properties of the tensile properties of these carbon fibers are quite far away from a commercial pan-based carbon fiber today, but they are comparable to some grades, and I think a realistic it would be realistic to achieve something in between glass fibers and commercial carbon fibers in near future. And the yield can be increased significantly if we add lignin or a flame retardant. And as my last slide, I would say that we have an ongoing project together with Chalmers University and Aalto University. And now we have been working just recently a lot with this stretching, and I think now we have learned how we can stretch these fibers in the carbonization to yield-oriented carbon fibers. So we're making progress, but research takes time, as you all know. And I would also like to thank my co-workers at RISE, Maria Sedin and Jenny Bengtsson and Tobias Könke for a very good collaboration. And with this, I would like to thanks for your attention and hope you have a couple of questions. Thank you.
Thank you, Andreas. Very interesting to listen. And yes, there are questions. First one is, how sensitive is the carbon fiber process to contaminants in the precursor, like craft-related ash?
Good question. I would say it's not fully ruled out, but too much ash is not good for sure. But exactly what limit in terms of if you want to quantify it, it's not fully ruled out.
Thank you. So more work to be done.
But ash content of the lignin below 1% is what we use, and it seems to work okay. But maybe it can be improved even more.
Next one is, how far are you from the mechanical properties of PAN-based carbon fiber?
Yeah, well, it depends on the quality there, but so these fibers typically have a modulus of around 60 to 70 GPa after carbonization at 1000 degrees. And a PAN-based carbon fiber sold standard modulus is around 200 to 250 in modulus. So it's a significant difference at this stage. But we have not really been able to optimize this since we have just recently started working with this type of equipment where we can stretch them. But I would say we would never reach at a certain carbonization temperature, we will not be able to reach the same. It's known that you can produce high modulus carbon fiber from cellulose, but then you need to do this graphitization step at very high temperature, and that is what you will need in that sense, probably.
Thank you. And what is the range of cellulose DP that could be used in this process?
Yeah, good question. Well, if we take first, we work with both this ionic liquid dissolution and cold alkali dissolution, and they behave very different. I would say the range of where you can, if you look under the DP, differs substantially. You can have a much wider window in ionic liquid or air gap spinning. It's more powerful, so you can dissolve cellulose with DP of, or say pulp viscosity of, say, 600 milliliters per gram, 500. But in cold alkali, you need to use much lower, typically around 250 milliliters per gram in intrinsic pulp viscosity, which is more or less the same as the degree of polymerization. So it differs.
Very well, thank you. What is the total concentration of lignin plus cellulose in the dope with approach 1 and approach 2?
In approach 1, typically 18%. If you dissolve it in MM acetate, which is ionic liquid, typically 18% if you sum up lignin and cellulose, but in cold alkali, it's around 6-7%. So it differs. That is one very good thing, but the problem with this ionic liquid is that they are very difficult to recycle and quite expensive solvent.
So challenges to challenge.
Yeah.
Yep. Is there a difference in using different types of lignins?
We have looked a little bit into this. We have tried to fractionate kraft lignin with membrane filtration and use the high molecular weight part, and you can also use that part. We have not seen any difference on the carbon fiber tensile properties, but we have some indications that a high molecular weight lignin may be good because it leaches out less. It's less risk of leaching during the spinning process. But I mean, in principle, you could also use organosolv lignin. Others have used organosolv lignin. We are working mainly with softwood lignin, but you can also work with hardwood lignin.
Thank you. And have you considered adding a third bio-based component for improving the properties?
I haven't tried anything, but it's a good idea. But then you also need to, that component will also need to be possible to dissolve in dissolvent systems. But I mean, that's an option for sure. That could be of interest, I think.
Thank you. What's the diameter of NFs that you are getting from this semi-continuous approach?
The diameter of the carbon fiber, single filament carbon fiber diameter. Well, we have tried many different precursors and so on, but the thinnest one we have produced the carbon fibers is around 5 microns, which is on par with the commercial pan-based carbon fibers. And actually, I didn't say it today, but the thinner the better usually.
Great. And so far the last one, how are the sulfur content affect the carbon fiber?
Good question. We don't really see that it affects that much from what we have seen, but I wouldn't really say that we have done a systematic study of it. But if you compare to others' work who have been doing the very similar thing, but with an organosolv lignin that doesn't contain sulfur, they typically get the same properties. So the sulfur may not seem to be detrimental, at least.
That was the last question so far.
Many good questions.
Yeah, indeed. And if anyone comes up with more, please type them in as well or save them for afterwards for the eftersnack. But thank you so much, Andreas, and I hope you stay in the webinar to listen to Åsa.
I will for sure.
Yeah.
Thank you.
Thank you.
I'll stop share.
Yeah. Hi, Åsa.
Hello. Hey. Can you hear me?
We hear you perfectly well.
Yeah, good. So I will also try to see my technical skills here in sharing.
For sure, they are good. And there you go.
Yes.
So please, Åsa, all yours. Who are you and what are you going to tell us about?
Yes, so I'm happy to be here and thank you for asking me to join this seminar. I'm then head of R&D here at Tree To Textile, and we are not working with lignin. We are trying to avoid lignin as much as possible, but of course we are able to hook up with this in a biorefinery concept. So we are really supporting the lignin industry here. However, I just wanted to tell you a bit about Tree To Textile and generally our journey. So where we are at the moment and how we got here. And I just need to, I can't see my whole slide myself. But I guess it's not a problem for you, right?
We can see it perfectly well.
Yeah, I just have. However, we are a growing company. We are a small startup, We are around 30 people at the moment employed by Tree To Textile, but we have a quite unique and large ecosystem of collaboration partners. And what you see here on this slide is also our owners. So H&M, IKEA, Stora Enso, and then large Stigson Invest. And our owners are also part of our ecosystem here. So we get a lot of support, both in resources or investments, but also in manpower. So we are really grateful for this. And where we are at the moment is actually here at the demo line. We are right now starting up the demo line. So it's located in Nymölla, Skåne. So a previous Stora Enso mill, which now belongs to Sylvamo, but we are renting our facility there. So it does not really affect us who we are renting it from. We also have a development in Gothenburg or Mölndal at RISE. And we are all the time trying to develop our process and put this into a patent portfolio. So this is how we actually develop or secure our knowledge and know-how. We are located, now I can't really point at this map here, but we are located in headquartered in Stockholm, where I'm sitting myself. And we have the demo plant in Skåne. And we are also building our own R&D center in Mölndal. So very close to RISE in Mölndal. And the purpose of this is to stay tuned with Mölndal and still have a strong collaboration with the RISE in Mölndal particularly. So we have a pilot line. So we produce cellulosic textile fibers in Mölndal already now with a capacity of 2 kilos per hour. And from this spinning, we are investigating further downstream how our fiber look like or behaves. But I would like to also explain a bit about our journey here. So we're actually started off before 2014 as a research project. And in this phase, I saw some of the participants in the participant list here that some of you were already part of the project at that time. And it was together with RISE. And we then 2014 established the company. And this was started by H&M, IKEA, and Lars Stigson. And at that time, the development happened at RISE in Mölndal, and they had this pilot spinning machine there, or we built it actually. So in 2015, this was up and running, and in 2016, we had the first industrial proof of concept in textile applications. And these applications were at that time a bed linen or a sheet of cotton and Tree To Textile mix, and also a t-shirt from our fiber. So this actually brought also some confidence into the owners, H&M and IKEA especially. And the owners also saw that they needed some scale-up partner, someone with the knowledge of cellulose and pulp. And then Stora Enso joined 2019. And they, at that time, started to do the drawings on a demonstration plant. So the next scale for us. And in 2021, we got a grant from the Swedish Energy Agency, which actually then also supported the decision to have the demo plant in Nymölla, and where we could actually start building the demo plant. And right now, as I said, we're in the midst of the starting up of this line. But as soon as the technology is proven, we are aiming at scaling up to full scale and commercial scale. So, but regarding the scale and the technology, I would like to move into what we really look like and what we have here. I just have to get rid of, I'm sorry for this. I have to get rid of the, yeah, good.
No problem. Take your time and reshare if you think that will help out.
I think I'm okay now. Do you see my slide still? Yeah.
Yeah, perfectly well.
Yeah. So this is more or less what the demo line looks like. Very basic drawing here, but what's coming in is a dissolving pulp. So pure cellulose comes in. We adapt this to shorten down the cellulose chains and adapt it into and wash it, and then it goes into the dissolution and the spin dope preparation. So in here we have we are combining the pulp with the solvent, which is the water-based sodium hydroxide with a small amount of zinc oxide in it. And this is done also under cold conditions, so a bit similar to what Andreas just talked about. And we have a rigorous stirring about for this. And then the spin dope as such is done. And it goes this way through filtration and deaeration. And then the spin dope is then ready to be regenerated into a textile fiber. So this is what's happening in this step. And what we have here, I mean, this looks a bit like the existing commercial fibers available, which is viscose. But in the viscose process, in this step, you have a sulfuric acid spin bath. And in our innovation here, we have an alkaline spin bath, which is playing with other phenomena than just decreasing the pH. So to have an alkaline spin bath is working more on the physical processes here. And we are then coagulating the cellulose out of this. What is then required is to have a water wash, a quite extensive water wash. But we, at the same time, we are saving a lot of chemistry in this bath, because if you have a sulfuric spin bath with an sodium hydroxide in the spin dope, you will have sodium sulfates precipitated out here, and these components will then be lost. So in order to save chemicals, it's much more clever to have this alkaline spin bath. And to save water in this step, we have a countercurrent water wash. So it goes neutral pH in this end and very high pH 14 in this end. So stepwise decreasing the pH. And then the fiber at the same time solidifies. And then we are drying the fiber and crimp it so that it gets a nice curl, and then we cut it and bale it. So it's very easy, bale in and bale out. And here we also have the heart of this setup. So the chemical recovery is really crucial to also save chemicals here, of course. And the principle, already as a research project, this process was evaluated many times based on, of course, mass balance calculations, but also life cycle assessments to really find the hot spots. Where do we have to work? And much of the work was actually focusing here in the spinning area to find the right coagulation bath. So then when we are looking at the chemistry and the total economy of the plant, it's very important. I mean, it's very obvious that money and sustainability in this sense actually is the same number. So if we are saving chemicals here, we are also saving the environment. But looking more into our LCA, the environmental performance here from cradle to factory gate. So the cradle here is, of course, the forest, and the factory gate is a staple fiber. So here we have performed LCAs continuously, but the latest LCA was done 2020 based on lab data. So it was lab data simulated up to full scale. And what I show you here is, so this is the Tree To Textile credentials here on climate impact. So this number, we are really proud of this number, 0.6. It's a very low number. And what we did actually to know what to compare with was that, I mean, you always can reach out to EcoInvent database, which are these numbers, but you still don't have the full transparency. And you can also look into literature. And if you look at the viscose here in the literature, it can vary from like 2 units here up to like 8. So it's a huge spread, and it all depends on where in the world you're producing it, what kind of energy source you have, how efficient your chemistry is, or chemical recovery is, and all these setups. So what we actually did in our LCA was to also include a virtual viscose plant. So we can then combine the same pulp as we have in our plant here, and we can also just compare the two processes. And by doing that, the viscose actually reached 1.8. So having the same pulp, which was a Swedish produced pulp, and just a different setup in the process to compare the viscose and the TTT or Tree To Textile process, the viscose then generated 1 or 3 times higher climate impact. So that's why we are extremely proud of this number. But I would also like to emphasize here that this is, I mean, we need to work on these numbers as soon as or update the LCA as soon as we have the demo plant up and running. So it will, new numbers will come. But I'm quite confident with this number, and we have been updating it internally. So I'm quite secure about it. What we're also comparing and looking at is the water consumption, of course, and especially when we are comparing ourselves to cotton, and also the eutrophication is also when we are comparing ourselves to cotton. So what we also do in our own business calculations are actually to see where do we really make, where can we do the best contribution in the textile industry. And when we look at the demand of cotton, we can actually see that our fiber can be blended in with cotton. It cannot fully replace it because it's a bit different, but it can blend in very well with cotton and broaden the cotton market. And the same, it can also substitute bad viscose. I would like to call it bad viscose because there are, as I said, viscose with very high climate impact, and these factories are normally in the shutdown phase at the moment. So if we can replace these at the market, we can actually also reduce the total climate impact within the textile industry. And just for fun, we did our own calculations, and I would like to share it just verbally with you. And this was if we replace but contribute to the cotton market by substituting some of the needed cotton. We substitute bad viscose, but actually the number that we had in the calculations are these. So it's not the worst viscose. And we can also in some markets take market shares from polyester. So we are not as strong in the fiber quality or fiber strength as the polyester. So we can't compare ourselves totally with polyester, but for some markets we can for sure replace polyester. And if we do that, do all these substitutions, plus adding new fibers also to the market, we can actually contribute to, if 1 million ton of Tree To Textile fiber is there in the market and replacing other fibers like I explained, we can actually contribute to a reduction in climate impact for the textile industry by 2. So 1 ton of Tree To Textile fiber actually gives a 2-ton reduction in climate impact. So this is something, I mean, the scale that we are playing with here. So it's we are really proud of this number here. And if I just continue here with where we are in the value chain and how we are working. So of course we put ourselves on top of this value chain, but so this is the Tree To Textile technology. That's the process that I told you about, which we are now starting up at the demo line. We are taking in a dissolving pulp, so we are not a pulping company as such. Out comes the staple fiber, and what we are doing now continuously is to evaluate this kind of fiber ourselves as well. So to learn how it's behaving in the downstream processing to textile and different products, and also the dyeing and the wet processing that is needed. And what we also have done is washing studies and also abrasion tests, mechanical testing of textiles to see how well we perform here together with or compared with other kinds of fibers. And of course, we also have to look into what will happen at end of life and take responsibility of this. So that's also what we are evaluating. But what's also very fun, under R&D, we're looking into very many sources of raw material for cellulose. So of course, wood is the one, the mainstream or the big bulk on the market. But still, you have different companies now producing textile waste pulp. So in Sweden, we have both the Renewcell and the Södra once more. We are also looking into agricultural wastes and also other kinds of cellulosic streams, residues or streams. So it's very important not only to have a nice number of the climate impact up here in our process, but we also need to foresee that we are not failing in this cycle of the value chain. And I just wanted to mention finally here a benchmarking study that we did comparing the lyocell, the viscose, our fiber, and also cotton. And what we did here was to start at the staple fiber of all these fibers and process them with the spinning of a yarn. So what you see here is the yarns look really the same. So it's the same yarn thickness and so on. And then we knitted textiles out of these. And we learned a lot from this study. And it also placed us, it was quite obvious that we are somewhere in between a cotton fiber and a viscose fiber. So it has actually a very similar natural hand feel as the cotton. And when you look at it, it has some luster, but not as much as the viscose. And some of the drape as the viscose, but really somewhere in between cotton and viscose. And this really puts some opportunities in our hands when it comes to what kind of market shares we are aiming at here. And this was what I wanted to raise today and introduce to you. So thank you so much for listening.
Thanks to you, Åsa. So inspiring. What a journey you're doing. And the questions are coming in. The first one is, have you tried different dissolving pulps, softwood compared to hardwood, different suppliers?
Yeah. Yes, we have been playing around quite much with different market pulps. So I don't remember exactly the number now, but we have been playing with, just as you said, both softwood, hardwood, craft, sulfite, different wood species, and so on. Yes.
And different challenges with all of them, or is it?
Yes, but I mean, we have some, most of them works fine. So we can make fibers out of most of them.
Thank you. First, very nice work. Congratulations. And in the water wash step after alkaline coagulant bath, how many times can you reuse the water?
I mean, it's recirculated. I mean, it's not really wasted. I don't know. We have it into our chemical recovery, and then we just take care of the salts. I mean, what's accumulated in the water wash is the salts, so sodium hydroxide and zinc. So we're recirculating the water.
Very good. And from a technical perspective, what has been the major challenge in the development of your spinning process?
The major challenges in the spinning process?
Yes.
I mean, it's the process is the challenge, but the major challenge, I think, I think I don't know. I mean, I was not part of the full journey here. So I started 2020, but until we had this countercurrent water wash and all that, so then it was of course a challenge to really have a good coagulation of the fibers, and also to have pure fibers out. So I think that's the main challenge that we have actually passed, I would say.
Right, thank you. And how does Tree To Textile fibers compare to viscose and cotton in recycling? Like Renewcell, for instance, they do recycling.
I mean, let's see. No, I wanted to look at this one here. I'm still sharing, right?
Yeah, yes, you are.
So here, I mean, we only have the process from pulp to staple fiber, and here is Renewcell, or rather here is Renewcell with their cotton pulp. So we can actually take in, or in principle at least, we can take in Renewcell pulp into our process. Is that the answer to the question?
Yeah, I think so. It's a clarification where you are.
And then, I mean, one option for Renewcell, if I should explain this a bit more, is Tree To Textile. It can be viscose, it can be lyocell. So, I mean, Renewcell can be coming in here to different processes, and as well as the Södra once more pulp as well. So, yeah.
Great. And a short one. What pulp works best?
I mean, it's right now we've been working very much with the Enocell pulp from Stora Enso, and that works very well for us. But that's also, I mean, it's not really fair, because that pulp is what we have actually played with the most, and also adapted our process towards. But what we see is that many similar pulps, so that's a dissolving grade pulp, many similar pulps, craft pulps, works really well for us. So I can't really say what works the best, but because it's not fair, we always can change some of the settings and then make other pulps work just as good.
Great. Thank you. And what is the tenacity? Is it comparable to viscose fiber, like textile grade?
Yes, I would say, and that's also why we see that we have a window there to actually take market shares when viscose plants are shutting down. So we are not. I mean, lyocell fiber is a growing fiber on the market, and it's stronger, but it has some other difficulties. And then we are not in the same range in the strength here. So
right, and a business strategy questions. What is your basic business strategy or main? Licensing GV is a joint venture, and or building your own fiber plants. What's the future plan?
Yeah, I mean, we are aiming at licensing, but on the way there, I think we need to have our own plant to learn more in the full scale. But this is not set yet, so we are not really. I can't really. It's not on my table to decide. But I think, I mean, what it looks like is that we will need both. But the licensing model is the long-term perspective. Due to that, I mean, we can't contribute to the reduction in climate impact to the textile industry if we are not big. So if we are just a niche fiber, a small fiber with a good carbon footprint, we can't make an impact on the big range if we are not having many plants. And that can also only happen through licensing.
Right, so under development.
Yeah.
And and have you noticed any big differences in the quality of cellulosic feedstocks that carry over in the spun fibers?
I mean, what we are happy with is that if the pulp as such is white, also the fiber is also white. So our process is not making any coloring on the cellulose just by letting the cellulose passing through our process. So this is actually a huge benefit to our process, that it doesn't generate any color on the fiber. So that's one way of seeing it.
Yeah, great. And clarification of the question before, where we see now the illustration, Tree To Textile fibers coming into Renewcell, and that would work.
Tree To Textile fiber coming into Renewcell.
Yeah.
So I still have this slide here. So end of life of Tree To Textile fiber, if that could come into the Renewcell process and generate a pulp, that's the question, I guess.
Yes, correct.
Yes, it's a cellulosic fiber, so potentially it could. And what we have seen is that we can actually recycle our own fiber. But I don't know, I mean, it's very, our fiber is very different from cotton. So I don't know, I can't explain, or I can't answer on Renewcell's behalf, but in principle, we can at least recycle our own fiber.
Very good. And we have a last one. First, chairing, thank you for your nice presentation. And what are the strongest properties of your fibers? Do you consider other potential and competitive applications besides textile? Is the price competitive? So a few questions together.
Yeah, but I think the price is one of our benefits, and that's also one of the missions from our owners to have low cost, low climate impact, and be a versatile fiber so that we can actually approach a broad market. And what you see here to the right is, I mean, we have a textile fiber, but we're also looking quite much into non-woven fiber. And with the non-woven fiber, we can include wet wipes and a totally different market.
Very good. And with that, we will say thank you again and end today's webinar. For those who are here watching us live, they are free to stay for another 50 minutes and talk to us. But for today, thank you. This was today's recording also. and we have listened to Andreas and Åsa and listened to a lot of questions. So thank you also very much to our audience, and wish you a further nice afternoon. Thank you.